Last week we talked about the discrete time Fourier transform, and we'll continue. Today we'll finish this. Okay. So I have a signal. Their discrete time Fourier transform will be omega. From the two examples, we saw that the discrete time Fourier transform is periodic. You see here we have cosine, and here we have cosine and sine, and the period is 2 pi. So the Fourier transform for discrete time is periodic with period 2 pi. Now, if I have the discrete time Fourier transform, it always has to be periodic. So you can see that it will be infinite with 2 pi. Now I want to find the signal. Okay, if I want to find signal, and here you can see that in frequency domain, this is like a bunch of sterns, kind of like a pulse train. Now, if in the frequency domain that's a pulse train, then what should we get for the time domain? If we first, let's just follow their formula. Or you can think that, how can I get your signal? Still remember that vector A is 5i plus 4j. If you want to get 5, that means your A in the product dot I. If you want to get 4, then you A in the product J. And the A is this combination. So now we are, you can also think that my X is the combination of your bases. So this will be 1 over 2 pi, the integration, only one period, your coefficient times the basis. So it will be 1 over 2 pi from 0 to 2 pi x omega e to the j omega n d omega. So we have 1 over 2 pi, and then, oh, this should be 2 pi. 2 pi, wait a minute, no. It's a pulse train, so nothing here. 1. And we integrate from 0 to 2 pi, so we get 2 pi e to the j omega naught n. From 0 to 2 pi, I only have values at omega naught. This gives you e to the j omega naught n. So now you see for the signal, if it is a complex exponential, then your frequency domain, there will be 2 pi times the pulse train. Oh, yeah, this is still 2 pi here. Okay. Okay, so from this page, you may observe something. First, let's see the differences between the continuous time Fourier transform and also discrete time Fourier transform. What are the differences? First, in the discrete time domain, n is a discrete variable, so n is only 0, 1, 2, 3, 4, 5. So I only have e to the j omega naught, e to the j 2 omega naught, e to the j 3 omega naught. Okay, so it'll be like omega naught, 2 omega naught, 3 omega naught, and so on. And then the discrete time Fourier transform is periodic, and the period is 2 pi. And then it is discrete in time domain, and now I got the continuous in frequency domain. So you cannot predict, you cannot expect that, oh, in this domain, I take the discrete time Fourier transform again, because it's from discrete to continuous. So there's no duality property for the discrete time Fourier transform. Okay? And the n must be an integer. So for the time scaling or the frequency scaling property is different. Let's see. If I compress if I compress a is greater than 1, then for continuous time Fourier transform in this way. But in discrete time Fourier transform, we have two properties. Okay, one is called downsampling, and the other one is called upsampling. And you will learn this in maybe the advanced courses like digital signal processing. But so far, you just need to know that this is downsampling. And here is upsampling. So what is downsampling? Here. So downsampling here, you can see that I only keep fewer samples for once we have this, but now you got a dn, so you only pick maybe if d is 2. So you only get a fewer samples here. So if you keep fewer samples, then that means that you can reduce the data computation and the bandwidth. Like you reduce data computation or the bandwidth. Where is the, maybe here. For example, that when do you do the downsampling? If you want to listen to the music smoothly, you can do the downsampling. So maybe green. For example, they can help you listen to music smoothly. Even on slow internet. And it is compression. So if you do the image compression, compression. Then if you have a few pixels, actually you are doing downsampling in space. If you do the upsampling, that is the other way. So upsampling, you will get more data. So instead of like only this signals, then you get more because you are doing the upsampling here. So you will add more samples. So in this case, you'll get a higher resolution. Okay. Right, but we won't talk more about this. Okay, they'll be in other advanced courses. Now, let's see the properties of the discrete time Fourier transform. Okay, so if we assume taking the Fourier transform in discrete time, then we get x omega. Sometimes in some textbook you may see x j omega. Okay, but here we just put omega. Linearity. Okay, similarly, that if I take the Fourier transform for 2, so I add these two signals first, and then take the Fourier transform. That means I can take the Fourier transform first and do the linear combination. So the application for this property, if I have xn, it's periodic. Okay, now the signal is periodic with period n. So if this is periodic, just like continuous time, if my signal is periodic, then I am still interested in knowing that what the Fourier transform is. So here, let's see the discrete time Fourier transform. And here we need to first write it down, this signal. It's periodic, so how can we write it down? How can we express the signal? The AK coefficients times e to the j k 2 pi over capital N. And your k is from 0 to n minus 1 because it's periodic with period n. So every n points, they'll get the same shape. Okay. Now let's see the Fourier transform, discrete time Fourier transform. For discrete time Fourier transform, all right. Let's write it down again. K from 0 to n minus 1, ak e to the j k 2 pi over capital N times n. Again, this is a linear combination of your bases. Like a is equal to 5i plus 4j minus 3k. Okay, those are the bases. and this is like your coefficient. Okay, so we take the Fourier transform for this part. You can put for the linearity as well. So that will be the linear combination of your Fourier transform. Okay, what is the discrete time Fourier transform for this complex exponential? Here. Right. So for this part, actually if you plot it, we have space, so it looks like 2 pi and it is periodic actually, so we'll continue here. Hey, so here's 2 pi, and then this is k omega naught. 2 pi k omega naught plus 2 pi k omega naught minus 2 pi minus 2 pi. And now you just times AK. So A naught, A1, A2, A3, A4 to here. Then you'll get summation k from 0 to n minus 1 ak 2 pi. The Fourier transform will be 2 pi times delta function, a pulse train, L is from minus infinity to infinity. Let's plot this. Before timing the multiplying the coefficient, it will be always 2 pi, right? Now I times AK. So I may have 2 pi A naught, and then 2 pi A1, and 2 pi A2, or like a 2 pi AN, and maybe 2 pi AN plus 1. And remember, it's periodic. So here we have 0. Oops. We have 0, omega naught, 2 omega naught, to here will be till 2 pi. This is 2 pi A naught, 2 pi A1. Here is 2 pi A2 to 2 pi AN. 2 pi AN is also called 2 pi A naught. Yeah, so in this case, I should get exactly the same as 2 pi A naught here. Okay. So this is 2 pi AN, which means 2 pi A naught. And this is 2 pi A n plus 1. which is equal to what? 2 pi a 1, right? So 2 pi a1 that I should get maybe. All right, so now we can say that the discrete time Fourier transform will be k from minus infinity to infinity, 2 pi ak delta function, well, the pulse train, okay, from here to here. Next, let's see the time shifting or frequency shifting property. If I have a delay in time domain, what happens in frequency domain? They change the phase, but the magnitude is still the same. If I shift in frequency domain, same thing, but this one we know that we are doing the modulation. So in time domain, at times the complex exponential or just cosine or sine. We will see that later. This is called modulation. So we will shift all period. Okay, so here, omega minus omega naught means to shift all period of your Fourier transform to the right. By omega. So you shift everything to the right by omega, by omega naught. Next, conjugation. So if I have a conjugate in time domain, in frequency domain, the Fourier transform, I also have a conjugation, but I also flip. But if the signal is real, when I do the conjugation, it is still the same. So the frequency, the Fourier transform is equal to you flip and do the conjugation. And this is called conjugate symmetric. When x is real, that means x is equal to the conjugation of x. That means the Fourier transform of these two should be equal. So that's why we have x omega will be equal to the conjugate of x and flip. So for this equation, that means if the signal is real, then the real part of your Fourier transform is an even function or odd function. Even or odd. And also the imaginary part. Even function or odd function of omega. The real part will be an even function. And the imaginary part is an odd function. Why? Okay, let's see this equation, this equality. This is because when x is real, then your Fourier transform is in this equation, which means the real part of your Fourier transform plus the imaginary part, that is the left hand side. Okay, so for the left hand side is equal to right hand side, the real part of x minus omega. And you do the conjugate, you do the conjugation. So here I have minus j imaginary part. So which means the real part should be equal to the real part right on the right hand side, that's minus omega. I flip. So this one, and I flip here the even function. Imaginary part, there'll be odd function. Okay. Next one, Parsifal's relation. The energy should be the same in time domain and also frequency domain. So this is called signal energy. Okay. Next, the convolution. Convolution in time domain. I will get the multiplication in frequency domain. Okay, if I have a signal, send it to a LTI system, then my output will be the convolution of your input and the impulse response. In this case, in frequency domain, it'll be easier to get. We just do the multiplication of their Fourier transform. Next one, differentiation in frequency. If I take the differentiation in frequency, every time I will generate the n in time domain. And if the signal is even, then the Fourier transform is also even. Even means x minus n is equal to xn. So for the Fourier transform, they should be the same. So the the left hand side, that's x minus n e to the minus j omega n, and the right hand side e to the minus j omega n. We know this is, suppose this is the Fourier transform x omega. How about the left hand side? Left hand side, let's do the changing variables. That L equals minus n. So I'll get the L from minus infinity to infinity. X L e to the j omega L. So this is also x minus omega. If you don't have any questions, let's see an example. I want to find the Fourier transform x1. Now, later on, I need to use the answer from A to compute the Fourier transform x2. And you can see that x2 is x1 plus what? x1 times n. Okay. So first, for the Fourier transform, that's n from minus infinity to infinity, x n e to the minus j omega n. Right, what is x1? Oh, should be x1, x1. So here, alpha to the n, un, and e to the minus j omega n. So for un, because it's a unit step function, so my summation is from 0 to infinity. I have a value 1. Okay. Alpha times e to the minus j omega overall n. And now when you do this, you need to check this ratio. Okay, see if this ratio is bounded or not. For this part, let's see the magnitude. Alpha times e to the minus j omega. This magnitude is alpha times the magnitude of e to the minus j omega. What is the magnitude of e to the minus j omega? You have 3 options. This will be 0, minus 1, 1, or none of the above. What is the norm or the magnitude of e to the minus j omega? 1. So here, because it is 1, you only get the magnitude alpha. So it's bounded. And it's x1 omega. It's x1 omega, but before that it should be a series. So 1 over 1 minus alpha e to the minus j omega. So that's x1. So for x2, actually it is n times x1 plus x1. So the Fourier transform is the Fourier transform of n times x1, and then the Fourier transform of x1. So when will we have this in time domain generate at n? That means in frequency domain, I'm doing the differentiation. So j d omega x1. Then you have 1 divided by 1 minus alpha times e to the j omega over squared. Alright, so it's time that you should wake up. Okay, so now here's our main dish. Let's see some discrete-time Fourier transform pairs. Okay, so first, let's see that in time domain, what is this? A sinc function. So similarly, that sinc function in frequency domain, then I should have a pause, rectangular pause. But for the discrete-time Fourier transform, we know that in the frequency domain, it's periodic. So I have a rectangular pause train. Rectangular pause train. Okay, and here is omega c and minus omega c. And we assume that your omega c, the frequency is between pi and minus pi. Okay. Next, what is this? Now, if I have, for this, because it's discrete, so you can see that my sinc function will be like this. Okay, so it is still like this, but discrete. Okay, so now in time domain, it is pause, and it looks like a unit step pause. No, it's a rectangular pause. If this is 0, this is 1, this is 2, and then till when? What is here? If I have u n minus u n minus capital N, here should be n minus 1, and then others, this will be 0, and here is 0. This is minus 1, and here's n, and also n plus 1. Okay. So in this case, what is a discrete-time Fourier transform? Right. Let me give you the answer, then let's take a break. That's sine n over 2 omega divided by sine 1/2 omega times exponential you can also think about that this, okay, times why do I have that exponential here? When will you see that in frequency domain, and I will have the complex exponential? It probably when you have a shift in time domain, right? If I have a shift in time domain, then I may have to time the a complex exponential. Okay, the Fourier transform is the same, but just the different phase. Okay, so it looks like here we also times the complex exponential. That means maybe like something in time domain I shift to like this one. Right. Then I will times this complex exponential. You can think about that how. Last week here it should be 1 over pi. Okay, in page 61 here for H4, the y here it should be 1 over pi. Right? It's not 1 over 2, 1 over pi. All right. Okay, so actually these are all 1 here. So this is the 1, 1, 1, 1, 1. So when I do the Fourier transform, discrete-time Fourier transform should be 1 times the basis. Okay, n from 0 to n minus 1. So in this series, it should be here. I have a fraction. How come it becomes this sinc function and shift? Okay, so here you may see this form many times, and we use the trick called half angle trick. We can use half angle trick to simplify this. Okay, because even that you just get this result, you still have no idea about how the frequency looks like. So what is the half angle trick? X. This is the 1 minus e to the minus j omega capital N. We can think of this as e to the j omega n over 2 minus e to the minus j omega n over 2. So I need to time e to the minus j omega n over 2 back. So in this case, this will be 1. Here will be e to the minus j omega n. Similarly, in the denominator, this do the half angle trick. So in the denominator, e to the j omega over 2 minus e to the minus j omega over 2. So I need to time e to the minus j omega times 1/2 back. So here you'll get 1, and here you'll get e to the minus j omega. And then you times 1 over 2j, 1 over 2j. So in this case, the first term times 1 over 2j, this will be the sine function. So we have sine capital N over 2 omega divided by sine 1/2 times omega times complex exponential e to the minus j n minus 1 divided by 2 times omega. So that's why you see like a sinc function and I have shift. Alright, so now to get this, that means that I shift in time domain by something. Right, so now I just form the y, this signal y is x of m plus k. Okay, so that means I shift to the left by k. So I shift to left by k. So if I shift to left by k, that means that my discrete time rectangle will be centered at n equals 0. Here I shift to left, so my rectangular will be like in the middle, okay? And here we have some, now, later. So the discrete time rectangular is centered at n0. Then we can use the time shifting property. So for the Fourier transform, that means that I have a Fourier transform x and that times e to the j k omega. Okay, and now we need to have assumption. y here comes to here, because we know that x omega is this one. We just derive it. Okay, but for k here, first we suppose that the n, this n is odd. Okay, so for example, 1, 2, 3. So this is 0, 1, 2. So I can shift to have minus 1, 0, 1. If I have a 5, 3, 4. So I can have a minus 2 and 2. So my terms should be odd. Okay, so here should be odd. So suppose n is odd. And with that, k equals n minus 1 divided by 2. K is an even number or odd number? Well, in this case, n is odd. Then k will be an integer, such that k equals n minus 1 over 2 is an integer. So that's why now k is n minus 1 over 2. Okay, and now you can see that for these two terms, they cancel out. They can cancel. So we can express that actually the signal y is u n plus k minus u n minus k plus 1. Let's plot the signal y. So if I have a discrete time rectangular center at 0, this is 0. I have, okay, so here if it's 0, 1, 2, 3, minus 1, minus 2, till k, here minus k. Then the discrete time Fourier transform, oh, and also the magnitude is 1. Okay. The Fourier transform is the sinc function sine 2k plus 1 divided by 2 omega and sine 1/2 times omega. Since k is n minus 1 divided by 2, that also means that n is 2k plus 1. Let's see this transform. Since sine theta is 0 when theta is m pi, m is integer. So sine, so sine, now here, there'll be n over 2 times omega. N over 2 times omega equals 0, which means omega is 2 pi m over capital N. M is still an integer. So that'll be 1, 2, 3, 4, 5. Now let's plot the Fourier transform. Okay, so for the Fourier transform, the peak is n. And now the first time when omega is 0, that's m equals 1. So here we have 2 pi over n. This one will be 4 pi over n and 6 pi over n until pi. And actually until pi and then periodic. Okay. Similarly here it's minus 2 pi over n. Here will be minus 4 pi over n until you get minus pi, and then you repeat, because remember it is always periodic. For this Fourier transform, when will we use this? Last week we talked about the filter, the low pass filter and high pass filter. Okay, so for the low pass filter and high pass filter, actually they just shift. They just shift here. Okay, what do I mean like shift? The high pass filter is this. Okay. Actually, this is minus 1 to the n times that. This is the low pass filter. You can think about that low pass filter is a sinc function. That's in time domain, because in frequency domain here. That's why it is low pass filter. But for the high pass, they just shift. Okay, kind of like modulation, a shift to the right. And actually in frequency domain it is periodic, so that's why you will see this rectangular in period. Okay. For the modulation, this shift property, we say that in frequency domain the high pass filter is like low pass filter shift by pi to the right. This is a low pass filter. Okay, for low pass filter, okay, from WC to minus WC, and in this pi, from minus pi to pi, and then it's periodic, so they got a bunch of rectangular signal. And if I shift, because I shift by pi, so here I shift by pi to here, it becomes a high pass filter. Okay. Now if I have a two rectangular pulse, two sinc function in time domain, what happens if I do the Fourier transform? Suppose omega 1 is less than omega 2 without loss of generosity. What is the Fourier transform? This one is rectangular pulse, right? Rectangular pulse. We done that last week. It will be what?完蛋！你知道答案，但是你不会念。Right. So if they are not equal, I have a trapezoid. Okay. Okay, so, but you can see what's the difference. Okay, so here we have a trapezoid. It's from minus pi to pi, but because it is in discrete time Fourier transform, so the difference is that it's periodic. So here later on, here I will also have another trapezoid here. And here you get omega 2 minus omega 1. And this point, what is that point? Omega 1 plus omega 2. And the height is omega 1 divided by pi. Remember, this is very important. It is periodic. Periodic with period. How much? 2 pi. If their frequencies are the same, omega 1 equals omega 2, just say that's omega naught, then the trapezoid becomes what? A triangle, right? And it's periodic, so here you will also get a triangle. Remember, that means here I have another one, another one, another one, another one. Okay? And this is minus 2, minus 2 omega naught. Here's 2 omega naught. The height is omega naught divided by pi. So 2 omega naught should be less than pi. Your omega should be less than pi over 2. Otherwise they will go outside. And then if you go outside here, you will have like over aliasing. Right, if you don't have any questions for this, now let's see the difference equations for the discrete time LTI system. For the discrete time LTI system, I need difference equations. Okay. We can relate the output to the input. Here is the relationship. For example, I have a system, and then I want to find Hn from this difference equations. And we can use properties of the Fourier transform. How do I find the impulse response? Or in time domain, we can think about frequency domain and then take the inverse Fourier transform. Or you can see that in frequency domain, if it is a rectangular pulse, but in this case, should be periodic. Okay, then in your time domain, then you know that this should be a sinc function. Okay, so if I want to find the frequency response, now I take the Fourier transform on both sides. Okay, so here the Fourier transform, the first term is y omega, and then minus 3/4. If I shift in time domain, what happens in frequency domain? In frequency domain, I still have our Fourier transform, but I have a phase difference. Here will be e to the j omega minus j omega. So here I have e to the minus j omega y. Similarly, here I shift by 2. So I have e to the minus j 2 omega. Right hand side, there will be 2 times the Fourier transform of your input. So you get your frequency response. That's the output, the frequency response of the output divided by the frequency response of your input. So you get 2 divided by 1 minus 3/4 e to the minus j omega plus 1/8 e to the minus j omega. That's in frequency domain. So back to the time domain. 1/2 pi. Integrate in the period 2 pi. Okay, this is like kind of like a linear combination of your bases. E to the j omega n d omega. All right, so if you check the table, you will see, here's the note. The Fourier transform of alpha to the n, un, this is 1/1 minus alpha e to the minus j omega. Okay, and in this denominator, I can have a factors. So actually h omega is equal to 1 minus 1/2 e to the minus j omega, and also 1 minus 1/4 e to the minus j omega. If I times that together, you get here. So for the numerator, I have a coefficient a and b. So in this case, it should be the same. Therefore, the numerator 2 is equal to 1 minus 1/4 times e to the minus j omega a, and also 1 minus 1/2 e to the minus j omega b. So what are a and b? From here, what is a and what is b? All right, so to find first, for example, to find b, which means I don't want this term, right? If I don't want this term, which means if this is 0, that'd be great. If this is 0, that means this should be 4. Correct? So this is 4. Okay. So therefore, to choose e to the minus j omega equals 4, then you can get b is minus 2. If you choose e to the minus j omega equals 2, which means this is 2, so everything is 0. So this one here is 2, 1 minus 1/2, 1 minus 1/2 times a should be equal to 2. So a should be 4. Okay, therefore, your frequency response is 4 divided by 1 minus 1/2 e to the minus j omega, and 2 minus 2 divided by 1 minus 1/4 e to the minus j omega, which means that in time domain, based on here, alpha, here you have 4 times 1/2 to the n, un. 4 times 1/2 to the n, un. Second term, minus 2 1/4 to the n times un. Okay? If the system, find the system response to this input. Which means, or find the output. Okay, so if I want to find the output, y equals x times h in frequency domain. So we have h, and now the x in frequency domain is 1 divided by 1 minus 1/4 times e to the minus j omega. And then your h so which is minus 4 divided by 1 minus 1/4 e to the minus j omega plus 8 divided by 1 minus 1/2 e to the minus j omega plus minus 2. Oh, here I have 1 minus 1/4 e to minus j omega square. Okay, so for this term, we have the Fourier transform. If I have n plus 1 times alpha to the n times unit step function, their Fourier transform is 1 divided by 1 minus alpha e to the minus j omega over square. Therefore, your output is minus 4 times 1/4 to the n un. Second term, 8 times 1/2 to the n un. Last term, minus 2 times n plus 1 alpha one-fourth to the n un. Right, any questions for this? I have this difference equations to the LTI system, discrete time LTI system. Similarly, okay, you can take the Fourier transform and you can find the system's response. H omega. At your time, maybe your turn. What is H omega? H omega should be Y omega divided by X omega, right? So what is this form? The fraction. What is Y omega and what is X omega? If I shift by 1 in time domain, in frequency domain, I will times e to the minus j omega and omega, right? Same thing here. So it should be 1 minus e to the minus j omega divided by 1 minus e to the, oh no, here should be 4 omega and then minus j omega. So how do I simplify this? Again, we can use the half angle trick. So we use the half angle trick to evaluate how system responds, at different frequencies. So let's do the half angle trick. What is half angle trick? Now the half angle will be 2 omega. So here we should have e to the j 2 omega minus e to the minus j 2 omega. And then we need to times e to the minus j 2 omega back. So they will cancel out. Not cancel out, there will be e to the 0, I get 1. And here you just add them together. In the denominator, similarly, e to the j omega over 2 minus e to the minus j omega over 2. Okay, times e to the j minus j omega over 2. Overall, you just times 1 over 2j, 1 over 2j. So you get sine. In the numerator, there will be sine 2 omega. Denominator, sine omega over 2 times e to the minus j 3 omega. Not 3 omega. 3 over 2 omega. Okay. This you can also compare with the discrete time Fourier transform of the impulse response if it is un minus u m minus 4. Next one, another LTI system. Okay, here is our difference equations. I need to find the frequency response of the system and also the impulse response. So if I take the Fourier transform, okay, here if I shift by 1, I will times e to the minus j omega. So in this case, your h will be 1 over 1 minus 1/2 times e to the minus j omega, which means in time domain it is 1/2 to the n un. Now find the response to 1 over 5 to the n. So what is the output? If the input is this, so the output will be the input times the system response, frequency response, or in frequency domain. Again, that in frequency domain, this is 1 divided by 1 minus 1/2 or 1/5 e to the minus j omega. Okay, so I should have 1 minus 1/5 e to the minus j omega. And also the h omega, we found that it's 1 minus 1/2 e to the minus j omega. Here is two coefficients. You should find the coefficient. A is 2 minus 2 over 3. And then B is 5 over 3. Therefore, you can get the output in time domain. For the signal cosine, what is the Fourier transform? Well, we can think about cosine using the Euler formula. Cosine pi over 2n, actually it is e to the j pi over 2n plus e to the minus j pi over 2n divided by 2. So they shift to the right and to the left, and the magnitude is 1/2. Well, I mean, wait. I mean, when you do the Fourier transform, in frequency domain, it's a bunch of stern. We need minus pi, and here pi. So I should pi over 2. I have 1 minus pi over 2 and 3 pi over 2 minus 3 pi over 2 and it's periodic. 2 pi over 2. So this is pi over 2 minus pi over 2, 3 pi over 2 minus 3 pi over 2. Okay, this is the signal in frequency domain. Okay, in math expression, cosine omega naught n that's pi times the delta function, shift to the right and shift to the left. But now it's periodic, so if I shift to the right by omega naught, and now you still need 2 pi L. And then shift to the left, omega plus omega naught minus 2 pi L. And your L is from minus infinity to infinity. And let's see, we also learned that in the beginning of today's lesson, the Fourier transform of e to the minus j omega naught n. This is 2 pi summation delta function omega minus omega naught minus 2 pi L. Because if I do the inverse Fourier transform, 1 over 2 pi, if I integrate from 0 to 2 pi, 1 cycle, this is 1 over 2 pi times e to the j omega naught n times 2 pi. So the output will be, since my input in frequency domain like this, so once I times h, I still have values at those points, but times something. Okay, that means the output looks like here. In pi over 2, 3 pi over 2, I have a value. Minus pi over 2 and minus 3 pi over 2. This is pi over 2, this is pi, and here is 3 pi over 2, minus pi over 2, minus pi, minus 3 pi over 2. And the value, the magnitude is pi times the frequency response at pi over 2. Here is pi times the frequency response at minus pi over 2. And so on. So what is h at minus pi over 2? H is here. Okay, so at minus pi over 2, we get one divided by 1 minus 1/2 e to the j pi over 2. 1 minus 1/2 j. And pi over 2, you'll get 1 divided by 1 minus 1/2 e to the minus j pi over 2. So it should be 1 divided by 1 plus 1/2 j. Therefore, the output is here. from the past 4 weeks. Okay, first we learned the Fourier series in continuous time and discrete time. And then if the signal is not periodic, we think about the Fourier transform in continuous time. And today we talk about the Fourier transform in discrete time. So now let's just have a summary or wrap up for these 4 different types. We call duality. Let's talk about the continuous time Fourier transform first. In time domain, this is a signal. That's the linear combination of your bases. Okay? I'll give you time to write, but first listen. Signal is a linear combination of your bases. To get your coefficient, you have your signal times your linear times your basis. Okay, again, A is 5i plus 4j plus 3k. Those are the bases, and I do the linear combination. To get your coefficient, that is your signal, in the product, your basis. And in the function here, we need to do the conjugation. So that's why you have minus. Okay. It is continuous time. So here, the signal is continuous. Periodic or aperiodic? Continuous. So continuous. So the signal is aperiodic because it's a Fourier transform. Okay, aperiodic, periodic. Right. Then when I do the Fourier transform in frequency domain, this is also continuous, right? Periodic or not periodic? This is still continuous. Periodic, aperiodic. Alright, so since in 2 domains they are continuous, so if I do the Fourier transform in frequency domain, this one, I can also think that in this domain it is with respect to time. So if I express that in time, I do the Fourier transform again, what happens? I will get 2 pi back to the original signal, but I reverse. That's the duality. So for example, if this is my signal, and then my Fourier transform is like that, now I will consider this Fourier transform, this figure, in time domain. Now in time domain, I do the Fourier transform again. Then I'll get 2 pi and times the original signal, and I do the reverse. So that I reverse that and then scale it. Okay? Right, that is the continuous time in Fourier transform. Next, let's see the discrete time Fourier series. For discrete time Fourier series, so Fourier series, well, at least first, it is not continuous, it's discrete, right? So first, it is discrete. Periodic or not periodic? For Fourier series, it is periodic, right? And so it's periodic for period n. So this is periodic. this you can also still think about the coefficients. This is a linear combination of your bases. Then how do you get the coefficient? Your signal times in the product your bases. And here, this is discrete or continuous. It is periodic or aperiodic. Periodic. Okay, so this is also discrete and periodic. Okay, so since in two domains they are discrete and also periodic, so I can take the Fourier series, okay, in the frequency domain, and in this frequency domain, I have this discrete as our time domain and do the Fourier series again. In this case, they will also reverse, go back to the original signal that reversed, but the scaling is 1 over n. So the fundamental frequency for the discrete time for the signal is 2 pi over n. Okay, so if we plot this, there will be in each interval there will be 1. Okay, and here I have a period. So the period is n. When I take the Fourier series, let's see the coefficient. Here the coefficient, you can see that the width, there will be 2 pi over n. Here the width is 1. And then I will take this here. Okay, so here will be like 1, 2, 3, 4, 5, because it is n. Take the Fourier series again. Go back to the original signal and then flip. Okay, reverse that. And this is 1 over n x minus k. All right, next we talk about the continuous time Fourier transform, discrete time Fourier series. How about the continuous time Fourier series? In time domain, signal is a linear combination of your bases. AK e to the jk omega naught t. Omega naught is 2 pi over t. Continuous or discrete, this signal. It's continuous, right? So it's continuous. Periodic or aperiodic? Periodic. Now in frequency domain, let's find the coefficient. The coefficient, again, we use the signal in the product, the basis. Okay, so in this case, in frequency domain, continuous or discrete, periodic or aperiodic. So this is discrete and aperiodic. Okay, so you see that in time domain it's continuous, in frequency domain it's discrete. So I cannot just like do it again, like I do the continuous time Fourier series and then do that again, because in frequency domain it is discrete. I cannot just do the Fourier series, right? What should I do? I should do something else. So I don't have a duality for this part. Like here, I have a duality. Okay, I can do the Fourier transform twice Here I can do the Fourier series twice, but not this one. Last one, the discrete-time Fourier transform. So for discrete-time Fourier transform, the signal, also that's the linear combination of your basis. Again, that sometimes you may see that x e to the j omega in some textbook, but here we just say that it is x omega. Okay, the signal is discrete or continuous, periodic or aperiodic. So first, discrete, aperiodic. Okay. And aperiodic. In the frequency domain, x omega that's x n e to the minus j omega n. Alright, continuous or discrete, periodic or aperiodic in frequency domain. Continuous, periodic, we did almost like 2 hours, right? Say, talking to you that in frequency domain, it's periodic. Like every time you need to consider it's periodic. Like also like in the beginning, we have some examples and you can see that they are like a cosine. Those are just periodic. And the period is 2 pi. Okay. Now you can think of that if I do the Fourier transform, that means the signal is aperiodic. Otherwise, I can do the Fourier series. Okay. So when we do the Fourier transform, there will be always like aperiodic. And if you are Fourier series, that's periodic. Okay. Now the question will be like in frequency domain, because continuous time, then it should be continuous. Discrete time, it should be discrete signal. But in frequency domain, what happens? For the continuous time Fourier transform, in frequency domain, it is still continuous and aperiodic. Discrete time Fourier series, in frequency domain, it is still discrete and periodic. But continuous time Fourier series, in frequency domain, what happens? They'll be opposite, totally opposite. You can see totally opposite. Continuous becomes discrete, periodic becomes aperiodic. Similarly, discrete time Fourier transform is discrete and aperiodic, but in frequency domain, it becomes continuous and periodic, 2 pi. Okay, for continuous time Fourier series itself, there is no like duality because you are from continuous to discrete. In discrete time Fourier transform, you are from discrete to continuous. So you cannot just do the discrete time Fourier transform again. But however, if you see these two together, it looks like I can take the Fourier series, continuous time Fourier series. And then this is like here. Okay, and then I can take the discrete time Fourier transform. Okay, again, I can take the continuous time Fourier series, and then discrete time Fourier transform. Then I probably will go back to the original signal. Let's see. So if I have a signal, first I can take the Fourier series. And then for this Fourier series, it is discrete. Right, so it is discrete. It is discrete. Then I can take the discrete-time Fourier transform. And actually I will get back to our original signal, but in frequency, and I reverse. For example, this is a continuous time signal. Okay, so I take the Fourier series. When I take the Fourier series, now I get what? The coefficient. Those coefficient. So for those coefficients, they are discrete and aperiodic. And you can see that the width is 2 pi over t. Now I can use the same figure, but just relabel that. So the width will be 1. So here is still like 0, 1, 2, 3, 4, but the width is 1. Now I take the Fourier transform, discrete-time Fourier transform. Now I got the continuous signal, and it is periodic. So after 2 pi, I will copy this here and here. And in the beginning, in time domain, the period is t. And then later on, I have a period that's 2 pi. Any questions for this one? All right. Now, let's talk about the fun topic and also the key concept or topic in this course. It's called the sampling. What is sampling? Okay. Sampling is just a process. What kind of process? The process of measuring the continuous time signal at specific points in time, like in in t naught, t1, t2, t minus 1, t minus 2, and so on. And when I measure that in this time point, I will get the result x of t naught, x of t1, x of t2, x of t minus 1. So we will use the constant time interval for sampling, like I use t. So every t, 2t, 3t, minus t, and I sample it. This means that x sample every t second. Every t seconds, and I'll get the discrete signal. That is the continuous time signal sampled at t. So suppose this is xt, and then we'll get the discrete signal. So this is our continuous time signal here, the blue line. Okay, for the blue line, and I sample it. So for example, like every 0.1 second, I sample it. So here you see that 0.1, 0.2, 0.3, minus 0.1, and so on. So this sampling time period is 0.1. And then you can see that if I only get those sterns, okay, this is just like copy paste here. This and the label here is like 1, 2, 3, 4, minus 1, minus 2, and so on. This is your n. Okay, this is discrete signal. The question is that if I give you this, can you reconstruct the signal perfectly like having this? looks like intuitively that you try to connect that, right? But maybe this is like that. This may be here. Right. For this signal, when I sample it, I also get the same stir, same magnitude, right? For example, if it is too narrow, for this signal, for this one, I may have this signal, okay? I may also have this signal. So the question is, how can I reconstruct our original signal perfectly? Therefore, given this discrete time signal, can we use it to reconstruct the original signal? Actually, in general, no. And it is impossible. Impossible to obtain the original signal x from this discrete signal. But we can approximate. For example, we can do the reconstruction by interpolation. So given this sampled at Ts, Ts is the sampling interval, or we call that sampling period. So we can use like a step function to reconstruct the original signal, which means that I have those sterns, right? Suppose those sterns are here. How do I know that from this point to the next point? So I use the step function. Okay, this is like a step function. For this step function, so I will create like this. That is one way. So the XR, this reconstruction signal is having all the step function. How do we express the step function? T minus K Ts minus T minus K plus 1 Ts. So this value times a step function. This value times the step function. This is one way. Well, intuitively, we can use this step function to reconstruct, right? But you can see that it is not that good because you'll get a lot of like step function. Okay. The other way you may think, okay, I have these 2 points, like here. How about I just connect linearly. So if I connect linearly, then we use piecewise linear functions, which means I can connect 2 points linearly. Right. In this case, your signal is here. The function fkt is or another way, we can do like a high order polynomial interpolation, which means the high order, so it'll be curved. And we call those techniques splines. And also that implies that there are so many different ways to interpolate samples and try to reconstruct the signal. So there's no way to perfectly reconstruct the original signal from samples. Okay. In this course, next week, we are going to learn sampling by impulse train. So what is impulse train sampling?